Let's do a practice problem. Yay. I have picked one out that illustrates a lot of the techniques that are used in the kind of algebraic approach to looking at functions and graphing, but also at techniques, the more qualitative approach that I find to be very helpful. So this is similar to something that appeared in a web assignment, a web assigned problem, and but I've put in numbers just to kind of straighten it out. So here's the function. The variable here is t, and it's a sum. And the first one is 9 times e to the t. So e to the t is the simplest function to do calculus with. And then we add into that 4 times e to the minus t. You might get a little insight, and you might not. This is the problem with doing these kinds of problems, is sometimes you just got to try stuff. And anyway, some people might find it more helpful to write this as I've just written it. Even if it's not helpful, it's good review. So what I've done is said, well, e to the minus t, that means 1 over e to the t. So this is the exact same function. And it's often the case that one of these is the more tractable form depending upon what it is that you're trying to do. One thing that this second one makes clear, and this is a very, very important thing about calculus, is that the functions that we use in calculus, e to the t, it doesn't matter what t is, that's never negative. So here we have a positive term, 9 times e to the t, and here we have a positive term because e to the t is never negative. And so we have positive over a positive. So one thing that we can see by writing the function this way is that this function always has a positive value. It can't even be 0. It always has a positive value. And that's a little bit harder psychologically to see because there's this prominent minus sign in the original statement, and so that might get you thinking about some negativity, but you got to think about where that sign is. And so there's our first bit of review. E to the minus t is 1 over e to the t, and e to the t is never negative, never even 0. And so there's the situation. Okay, now one other thing I'd like to do, and in many cases, this is enough. It's not going to be enough for this problem to really understand the graph of this function. But in some cases, this is. And I'm going to kind of color code this as follows. What we have here is 9 times e to the t plus 4 times e to the minus t. And I'm going to do very rough graphs of these two terms. And when we add them up, you'll see that that actually tells us quite a lot about how this function behaves. So the first one, 9 times e to the t, is basically 0 for a long time. You know, e to the minus 10 is undetectable. And then it jumps up really quickly. And so that's the way the exponential function works. It's nothing, and then boom, off it goes. And so there's the situation. The other function is a 1 over e to the t or e to the minus t, either way. And so that looks like this. It starts off being very steep, and then basically it's 0. So what you have here, the red is basically 0. So in that part of the graph, the green will dominate, and over in this part, the green is basically 0, so the red will dominate. So that's telling us that we're having a graph kind of like this. This is purely qualitative, but in fact, it might answer the question that we're looking at here. So I've taken the two terms, and this only works because they're both positive, but hey, take advantage. And so here's already a rough graph, and based on understanding of the behavior of the exponential function. And so, you know, if I put this on an exam, a traditional sit-down take-home exam, and you did this, I'd give you a 5 out of 10 or something, maybe 6 out of 10, because this demonstrates a lot of insight into what the function is. You probably do want to know exactly where this minimum is, and you probably do want to go through the practice of seeing where the function is increasing, where the function is decreasing, where the concavity changes. Hint, hint, it doesn't. And so we'll go on. So now we're going to go and do the algebra portion of this kind of situation. And so, I've got f of t up here. And so I'm just going to take the derivative. And part of the reason I picked this is that this function involves taking one of the derivatives that is most often done incorrectly. So I want to remind you how to do it correctly. And so for the first term, a constant times a function, the derivative is just a constant, and the derivative of e to the t is e to the t. So easy teasy, so that's 9 times e to the t. Now in the second part, this is where people kind of run into trouble, because it's easy to overlook the fact that this is a composition. You took t, without sugar please, no. You took the variable t and you negated it. That's a function. It's a very simple function, but it is nonetheless a function. And so when you do the next step, which is to raise e to that power, boom, you're in chain rule land. And so you have a composition of functions, and so the derivative is the product of their derivatives. And in this case, the derivative of minus t, remember t is the variable, the derivative minus t is -1. And so the value that you get here is minus 4 e to the minus t. This is a very easy mistake to make, is to ignore that minus sign, and then you miss this minus sign, and then everything you've done is wrong after that. So, okay, so there's the derivative. Now we want to know where the derivative is positive and where the derivative is negative, and I'm going to show you two ways to do this. One is very straightforward, and the other's a little fancier, but it's a lot easier. So method 1, to find out where a function is positive, you need to find out where it's 0. So what I'm going to do is set 9 e to the t minus 4 e to the minus t equals 0. So that will give me the critical point. And then we get to do some algebra, so I'm going to have 9 times e to the t is equal to 4 times e to the minus t. That's just adding the same thing to both sides. And now it might get a little bit fancier, so I have that e to the t is 4/9 times e to the minus t. We're still kind of far from solving this. When you have the variable and the exponent, the most natural thing to do is call your friends. The most effective thing to do is to use the natural log. So let's start taking natural logs. So on the left here, we've got t, and on the right we have the natural log of 4/9 minus t. So the natural log of a product is the sum, of the natural logs. Natural log of 4/9 says, yeah, well, da-da. And then we have minus t. So we end up with 2t is the natural log of 4/9. And now I'm going to pull a little bit of magic. That means that t is plus or minus the square root of 2/3. What? Yes, because let me put in the missing step, which is that t is 1/2 times the natural log of 4/9. Ooh, I put an extra square root in this other one. We're going to fix that. I shouldn't have done it in my head. Don't do stuff in your head. What I have here is that t is 1/2 the natural log of 4/9. And using the logarithm laws, this is the natural log of the square root of 4/9. Now, you can only take natural logs of positive numbers, because what you're taking natural log of is a value of e to the t, and you're trying to find the exponent. And so there is only one relevant square root here, and so that's the natural log of 2/3, which is approximately 0.69 minus 1.10. It's worth knowing natural log of 2, natural log of 3. So this is approximately minus 0.41. So there's the critical point. The exact value is, where to go? At the natural log of 2/3, and there's an approximate value. So there you can read it. Okay, now, so that is the more straightforward method. Just as they say in the quantum mechanics world, don't think about the philosophy of all this weird stuff that happens in quantum mechanics. Just shut up and calculate. That's what we've done here. Shut up and calculate. So now let's think about the philosophy. And the philosophy is this. I'm not really thinking about the philosophy, but let's see what we can find here. Let me write it what it is I'm trying to do again. I'm trying to determine the sign of 9 times e to the t minus 4 times e to the minus t. And now I'm going to do something weird, but appropriate. And what I'm going to do is rewrite this to get rid of that pesky minus sign. So what I'm going to do is multiply it by e to the t over e to the t. We never have to worry about e to the t being 0, so this is just another name for 1. And when we simplify that out using the distributive law, what we find is that 9 e to the 2t, it's a fraction, excuse me, on top is 9 e to the 2t minus 4. Doesn't that look easier? 9 e to the 2t minus 4. And the bottom is e to the t. Now, this is the right way to think about doing derivatives, is you say, oh, look at this, I got something on top, and the bottom is never negative. So as far as looking for the sign of the derivative, I could ignore the bottom of this. So by introducing this other factor, I have made the problem much easier, because I can ignore the bottom of this fraction because it's always positive. All right, so this is we're looking at the sign, and so this is the same sign as, that's one of my favorite phrases. I'm sorry, I said it incorrectly. I wrote it incorrectly. It's the same sign as 9e to the 2t minus 4. So if we're thinking about signs, this doesn't change the sign. So if you're thinking about signs, just ignore that, because it's a factor. If a factor doesn't change the sign, you can just ignore it when you're looking for signs. If you need to plug in a value here, which we will in a minute, well, not for this function, but for this function, well, then you need to worry about the exact value. But you don't need to worry about the exact value if all you're looking for is the sign. Okay, so we've got now, this is the same sign as 9 times e to the 2t minus 4. So now we set that equal to 0. I've skipped a step here. So we have e to the 2t is 4/9. And once again, that means that 2t is 2/3. Square root of 4/9. I'm sorry, natural log of 2/3. See, when you do stuff in your head, you do it wrong. Okay, so I need the sign of this. I set it equal to 0. I skipped a step here, and now I've got e to the 2t times 4/9. I'm sorry, e to the 2t equals 4/9. So taking natural logs of both sides, 2t is the natural log of 2/3. Okay. So I'm sorry, that's t is the natural log of 2/3. 2t is natural log of 4/9. There we go. So now we know the critical point. There are two different ways of fighting through the algebra. One I really like, because when we apply the mean value theorem into using derivatives and the way that people really use them, we need to know the sign of the derivative. If you're doing the tangent line approximation, you need to have the value, but we're not doing that. We're doing the graphing stuff, which would include all the max, min, and other kinds of things. And so all we need is the sign. So we've got the sign. Sign changes at natural log of 2/3. And so there's the deal. And so what we have is that with this change at natural log of 2/3, the function changes from decreasing to increasing. So that's this little diagram here. Okay. Next. Second derivative. Ooh, how bad could it be? Let me remind us what f prime of t is, which is 9 e to the t minus 4 e to the minus t. And now one of these strange things that happens in calculus, which is a calculus 2 topic. So I'm not going to explain it. I'm not going to explain, I mean, I can explain why it's true, but I'm not going to go into the depth of the complex hyperbolic mixed match Scherr-Mulligan theorem. Anyway, so I'm going to take this derivative, and again, the derivative of 9 times e to the t is just 9 times e to the t. But now we have the derivative of 4 times e to the minus t. And again, that's that chain rule situation. And so we're going to bring out a negative factor, and we're going to end up with 4e to the minus t. And you might notice that the second derivative is equal to the original function. Something deep going on there, but it's not part of this course. So anyway, and you know what we care about? Well, that's all. Oh, that's so sweet. Oh, so thank you for thinking of that. What we care about is that because the original function was always positive, the second derivative is always positive, and the graph is always concave up. So the graph is always concave up. Now, what I'm saying is that this shape was correct, because here we have the functions decreasing, and then it's increasing, and it's always concave up. And so there's a minimum right there. And we know now the the t value where that minimum is natural log of 2/3. Okay, so the final tricky part of doing this is it's fine to know where the minimum is, but what's the minimum? So this is always something that you would need to do in almost any place where you would be applying this kind of reasoning to some kind of function. We've seen this with the surge functions. And so anyway, so let us find the exact minimum. And what we have to do then is find f of the natural log of 2/3. Now, does that seem weird or what? Anyway, it's not that bad because f is full of exponentials, and I'm going to use this form. So e to the natural log of 2/3, that's just 2/3. E to the natural log of 2/3, that's just 2/3. So what we have here is 9 times 2/3 plus 4 divided by 2/3, which is times 3/2. I don't like to do arithmetic in my head, but we're running out of time. So we can get a value out of that, which is 3 times 2 plus 2 times 3, which normal people call 12. So the minimum for this function is at the following point. I'm sorry, I didn't draw that right. I'll draw it more correctly here. So there's the basic shape, and the minimum is at natural log of 2/3, comma, 12. And so there's the minimum value of that function. And so that's pretty close to what we figured out here just by knowing stuff about exponential functions, but it's also something that we can support analytically now. Now, I think that all graphs ought to have a scale, and so I'm also going to throw on one more point, which is f of 0. This is a graphing nicety, but f of 0 is 4 times 1, I'm sorry, 9 times 1. 9 times e to the 0 is 9 times 1, plus 4 over e to the 0 is 4 divided by 1, and so that's 13. So there's another point I'm adding on this graph, which is 1, 13. Remember, I'm going to scan this so you don't have to worry about. So now we know what the scale is. So that we know the vertical scale of 1, and again, natural log of 2/3 is about minus 0.41, and so we've got things done there. So let's see what we did. We reviewed some of the properties of exponential functions, reminded ourselves that they were always positive, looked at the basic shape, which is almost like a square. It's like nothing and then off to infinity or beyond. And so we looked at the shapes of the two terms and were able to say, hey, over here the green one's mostly zero, so we'll just do the red one. Over here the red one's mostly zero, so we'll just do the green one. And then we took some derivatives. We did one of the most commonly done wrong derivatives because of forgetting the chain rule necessity because of this minus sign. And then we took the derivative. We found the critical point two different ways. Either way is fine. I prefer to think about signs because that's what we're really interested in, but sometimes you got to do more. And then we actually have a pretty legitimate graph because we have the scales. So interesting function, and we'll be able to maybe do more with it sometime. Thanks.